using the unit circle definitions. So we want to find the sine, cosine, and tangent values for each number that's given here using our new unit circle definitions. So we'll start with the number pi over 4. Well, we go to the unit circle, we start at the point 1, 0. Pi over 4 is positive, so we're walking counterclockwise. Of course, we don't really have to think about walking. We can simply think about rotating in the amount of pi over 4 radians, which is the same as 45 degrees. I need to find the coordinates of this point. What I can do is drop a perpendicular here. I can see I have that 45, 45, 90 triangle. And this picture should look familiar to you. We already determined from the wrapping function that in this picture the hypotenuse would be 1 and each side would be root 2 over 2, which means the coordinates of this point are root 2 over 2, comma, root 2 over 2. Well, that's all I need to write down the trig values. Sine pi over 4 gives me the b coordinate, root 2 over 2. Cosine pi over 4 gives me the a coordinate, also root 2 over 2. Tangent pi over 4, well, that gives me the ratio of the b coordinate to the a coordinate. So what I'll have to do is I'll have to take root 2 over 2 and divide it by root 2 over 2. Well, hopefully it's pretty obvious to you that anything divided by itself is just 1. Or you could work this out by clearing the little fractions, multiply top and bottom by 2. That'll give you root 2 divided by root 2, which of course is just 1. And so we've found our three values. Let's try it for the number 5 pi over 3. Let's see, 5 pi over 3 is positive. I'm walking around counterclockwise. Really, though, I just need to think about rotating 5 pi over 3 radians. It's one of our memorized angles. It's 300 degrees. So rotating 5 pi over 3 radians is the same thing as walking 5 pi over 3 units. I need to find the coordinates of this ending point. Well, again, I can drop a perpendicular. If I rotated 5 pi over 3 radians, which is the same as 300 degrees, that means this little angle here, the reference angle, is 60 degrees. I have here a 30, 60, 90 triangle. Be careful when you fill in the sides. Normally, we've been putting 2 along the hypotenuse. I can't do that because I'm on the unit circle, so I know that that distance is 1. It's a radius distance here in the unit circle. So I'm going to have to make some slight adjustments. In the generic 30, 60, 90 triangle, the short side is x, the medium side is x root 3, and the long side is 2x. Well, what I know in this picture is the long side, the hypotenuse. The 2x is what's equal to 1. Obviously, dividing both sides by 2 means that x is equal to 1/2. So what that tells me is the 30-degree side, which is right here, must be 1/2, the x value. And the 60-degree side, let's see, that would be 1/2 times the square root of 3. Put a 1 underneath, and that's going to make square root of 3 over 2. So this side here is square root of 3 over 2. It's obviously a negative since it goes down, so I'll put negative root 3 over 2. But I have my coordinates now. 1/2 comma negative root 3 over 2. With that information, I can write down my three trig values. The sine function sends me the b, the second coordinate, so negative root 3 over 2. The cosine function sends me the a, 1/2. The tangent function sends me the ratio b over a. So I would write negative root 3 over 2 divided by 1/2. I can clear out the little fractions by multiplying top and bottom by 2. And then what I'm left with is negative root 3 over 1, which simplifies to just negative root 3. And so there's my three values. So is this the only option we have now? Of course not. Our old definitions still work. In fact, personally, when I'm dealing with angles that are multiples of 30 degrees or 45 degrees or 60 degrees, I use the reference angle definitions. If I wanted to figure out sine of 5 pi over 3 quickly, I would go to the xy plane. I wouldn't draw a unit circle. I would go to 300 degrees. I would know that my reference angle is 60 degrees. I would drop my perpendicular, and if I'm not constrained by the unit circle, then I can use the easy labeling for the 30, 60, 90 triangle. The 1, the root 3, and the 2. Of course, this would be negative here in the fourth quadrant. And then the sine function, just use SOHCAHTOA. opposite negative root 3 over 2. And here's the answer right here. So if you're given the choice, feel free to just do it this way. Having said that, here's where the unit circle definitions really shine. Take a look at this input number, 3 pi over 2. Once again, I want to find the sine, cosine, and tangent ratios. I start here. I walk 3 pi over 2, which is the same as rotating 3 pi over 2. 3 pi over 2 is 270 degrees. So I know I'm going to end up right here. That's a super easy point to label on the unit circle. It would simply be the point 0, negative 1. Just like that, I know my three trig ratios. The sine ratio gives me the b. The cosine ratio gives me the a. The tangent ratio gives me b over a. Can't divide by 0, so that comes out undefined. Once again, we've got our three values. I would say definitely use these unit circle definitions when you're dealing with quadrantal angles. It's the easiest way to go. Lastly, what about the calculator? How do I find just the sine value for the number 5? Well, there's no change. We have learned that the number 5 can simply be thought of as 5 radians. And so as long as you're in radian mode, the calculator will give you the correct answer. Let's see, I am in radian mode here, so I just have to type it in. And there it is, sine of the number 5, negative 0.9589. And for cosecant of 5, well, we're going to type that in the same way we always have. We'll use the reciprocal of the sine function. So we'll type 1 over sine 5 for an answer, negative 1.0428. You will be happy to know that these are the final definitions for our trig functions. Thanks for watching.